Hello everybody, this is Nicholas Zabaras and we continue our lectures on statistical computing and machine learning. Today the lecture will be on random variable generation, so that's a very important ingredient to allow us to implement the Monte Carlo estimators that we saw in the last lecture. So let's see what the topics for the lecture today will include. So we will motivate, of course, why we need this sampling method, starting with some brief review of the Monte Carlo estimators. I will tell you how to sample from the discrete distribution and also from simple continuous distributions where you know the CDF, the cumulative density function. And then we will discuss a little bit about transformation methods, which are basically methods that allow you to start with sampling from some simple distribution like a uniform distribution, and then using some transformations of these uniform random variables that somehow will allow you to generate realizations from very complex distributions. We will apply these techniques in the context of the multivariate Gaussian, and we will see the so-called Box-Muller algorithm. And then we will start discussing in the lecture today this whole family of algorithms that goes under the name rejection sampling or accept-reject algorithms. And those algorithms are very important, not because they're very useful in high dimensions, because they are not, but they're very important since they introduce ideas that they're fundamental to many of the more advanced and more recent sampling algorithms that we will discuss in the lectures ahead. Okay, so the goals for the lecture today will be to learn how to sample from the discrete distribution, from some simple continuous distributions, become familiar with the use of transformation methods, and then being able to use the accept-reject algorithm and variants of that in simple problems. Okay, so let me remind you what we had in the earlier lecture. We wanted to compute this expectation of f of x under some distribution pi of x, and the idea was to use a Monte Carlo estimator for that. So before I show you that review, let me just say that generally speaking, in the context of what we will see today and in the coming lectures, the distribution pi of x doesn't have to be normalized. So this is very helpful because this normalization factor that you see here can be rather difficult to compute, even with Monte Carlo estimation, because maybe x is very high dimensional. So the good news are the fact that in most sampling algorithms you don't need to know the normalization constant of pi of x to sample from pi of x. Okay, so here is the Monte Carlo estimator. We wanted an approximation of the expectation of f under pi. So what we need to do is sample IID from the distribution pi and then form this empirical mean, and with the law of large numbers, effectively we have a good approximation of the exact expectation of f of x under the distribution pi. Okay, we discussed that this estimator is unbiased, and then the rate of convergence was 1 over square root of n, and even more importantly, the rate of convergence is independent of the dimensionality of the problem. So that's very important, and of course we discussed the differences with deterministic approximations of this expectation and of integrals in general, so I am not going to review those today. So here is the algorithm, right? We sample from pi of x, we evaluate this approximator that I call here f hat, that's an approximation of the expectation of f under pi. And then this estimator is unbiased, so the expectation of f hat is the true expectation of f under pi, and the variance of the estimator is the variance of f divided by n. That's what we have seen, and of course the only thing that is missing that will allow you to go and implement this today is the fact that we have not discussed how to take samples from some general distribution pi of x. So we will need to cover this in the lecture today. I also want to remind you, because I may use this notation again in today's lecture, we introduce this empirical measure pi hat subscript n of x. So you can think of this as a representation or an approximation of the distribution pi of x using samples. So this empirical measure, it's, as you notice, a mixture of delta functions, each of them centered at samples from the distribution pi, and each of them weighted with the same weight 1 over n. So what we saw in the lecture last week was that if you want to compute, let's say, expectations under pi of x, if instead of pi of x you use this empirical measure, then immediately you come up with the Monte Carlo estimators of those expectations. So the idea is, from now on, if you need to compute any Monte Carlo approximations, what you need to do is, where you have pi of x, use this empirical measure, and that will lead you to the Monte Carlo estimators of interest. So for any function f of x, the expectation under the empirical measure is exactly this. All right, so this is not an approximation. If you compute the expectation under pi hat subscript n, you get the Monte Carlo estimator, and this is an approximation of the true expectation of f. If you want to be a little bit more mathematically correct, you can write, so this is the expectation under the empirical measure pi hat. So if you take the expectation of this with respect to the true distribution pi of x, this returns you the true expectation of f under pi, because we said this is unbiased, and the variance turns out to be the variance of f divided by n, and these are all things we have seen again in the earlier lecture. And again, we have not addressed how do we get those samples under some distribution pi of x. And that's what we will discuss today. So let me just say that in the lecture today and all the lectures on Monte Carlo methods, we're going to assume that we have the means, so we have the software and the algorithms to sample from the uniform distribution from 0 to 1. And most computer platforms, they do have what is called a pseudo-random number generator for uniform random variables. And I call this a pseudo-random number generator because literally these generators use deterministic algorithms to produce samples from the uniform distribution. Now, that is not an issue, and we can consider those samples still being IID, but you can imagine there are some pathological situations where you may find yourself that the samples generated from these pseudo-random number generators may not be at the end of the day IID. But right now this is not an issue, and we're going to assume that you know how to, you have the means to sample from the uniform distribution. And the whole objective of the lecture today will be, if we know how to sample from the uniform distribution, how do we sample from the Gaussian, or how do we sample from the gamma or the beta or any other distribution? And that's what we will try to start touching upon in the lecture today and the follow-up lectures. All right, so let me move to the discrete distribution, which is one of the easiest to learn how to sample. So let's say we have a distribution that x can take the values 1 to 3, and let's assign some probabilities. Probability of x equal 1 to be 1/6, x equal 2 to 6, x equal 3, 1/2. And the first thing you're going to do is you're going to define the CDF of x. And here is a formal definition of the CDF of x. And I'm using, as you notice, the indicator function here. So try to convince yourself that you understand how this definition looks like. And maybe what I can do is I can move to the next slide just to show you for another discrete random variable with 5 states how the CDF looks like. So my random variable takes values 1, 2, 3, 4, 5. And you notice the CDF is 1, and then it jumps by the probability P1. That's the probability of x equal to 1. So the CDF remains constant until the state 2, and then it jumps by P2, and then it jumps by P3 until basically I reach the value of 1. And effectively, this equation that I have here, it's nothing else but a more concise way to write down the CDF or the cumulative density of a discrete random variable, in this case with 3 states. All right, so how do we sample from a discrete random variable? I am going to write you the algorithm mathematically, and then we will visit this graphically, and we will come back to this equation. So here's what you need to do. You're going to sample a uniform random variable from 0 to 1, and then you're going to invert the CDF for that particular value of u. So you're going to find the x that inverts the CDF, and that x is actually going to be the infimum or the minimum x for which the CDF at x is greater or equal to u. Okay, so it will turn out that this fx inverse of u, it is a sample from the discrete distribution pi of x. Now, I realize that just looking at this equation, you say you're going to take, the minimum of x of the discrete values, right? The x can take discrete values, so the minimum of x for which the CDF is greater or equal to u looks a little bit cryptic. So let's try to visually understand what exactly that means. Okay, so I'm going to work with this discrete random variable that takes 5 values with the probability shown on the top picture. So what we're going to do is we're going to define the cumulative density function exactly as I had before, but here I'm writing it explicitly. So pk, this is capital P and this is little p, so pj is the probability that x equal to j. These are the probabilities of the discrete states. Capital P of k is the CDF. So I'm defining capital P subscript k to be the sum of pj's from j1 to k. Of course, p of 0 equal to 0 and p infinity equal to 1. So let me give you a graphical representation of what this cumulative density function looks like. So let's say that the state 1 comes with probability little p of 1, the state 2 comes with probability p of 2, then p1, my density function, let's say from 0 to 1 is 0, then from here to there is capital P1, which is the value P1, and from 2 to 3 it is P1 plus P2. Okay, so this is what this equation is all about, and that's the cumulative density for my discrete random variable, and this is a formal way to write it down. So you can actually appreciate the fact that this capital P of k, because it is the CDF, but it's really nothing else but the probability that x is less or equal to k. And let me just show to you by taking as an example P2. So we said P2 is P1 plus P2, all right? You will appreciate that this is the probability that the discrete random variable takes values less or equal to 2, because that's the probability of x equal 1, and that's the probability of x equal to 2. Now, we remember the task is to take a sample from this discrete random variable, and I wrote before the equations, and I said we're going to sample a u from 0 to 1, and we're going to define the corresponding sample from the discrete random variable to be the sample xk, where k is the minimum of from all possible k's, for which u is less or equal to capital P of k. All right? So again, I am going to sample a u from 0 to 1, and then I'm going to define as my sample to be the state k, for which u is less or equal to capital P of k. So let me try to decompose this to some simple geometric aspects. Let's say that u, your random variable that you select from 0 to 1, is this particular value that brings you to this interval 2 that you see here. Okay? Now, you appreciate, looking on the schematic, that this u is greater or equal to capital P1, and it is less or equal to capital P of 2. And if I follow this statement here, it says select k to be the minimum of all the k's for which u is less or equal to pi subscript k. This is capital pi, that's my CDF. And of course you can see here that the smallest k for which u is less than capital pk is nothing else but k equal to 2. And according to my discussion up to now, then your sample will be basically x equal to 2. Okay, so that's my inverse CDF algorithm. You sample u from the uniform distribution, and then what you do is you find the k for which u is less or equal to pk, and you will select the minimum k for which this is valid. So in our example, that k is equal to 2. All right, so that's the algorithm. All right, so we're going to draw u from the uniform distribution, and we're going to select the minimum k for which u is less or equal to pi of k. Let me give you a formal proof of this so that we don't have any confusion. Okay, remember that the algorithm that I generated is, right, I told you that I am going to take x equal to k when u is between pk minus 1 and pk. So effectively, the probability that u will be between capital Pk minus 1 and capital Pk is equal to the probability of x being equal to k. Now the question is that probability of x equal to k equal to little p subscript k? Because that's my probability for the k state for my discrete random variable. So let's see that. This is my definition. This is what the algorithm does. Because u is a uniform random variable with PDF1, I can write this as the integral of du from capital Pk minus 1 to capital Pk. So I can write this as capital Pk minus Pk minus 1. I use the definition of the CDF. This is the summation of the Pj up to from 1 up to k. And that's the summation of the PGA from 1 to k minus 1. And if you subtract the 2, you get that this is equal to p, little p subscript k, which is the correct probability density. So effectively, the algorithm that I describe does give you the correct, it gives you samples with the correct probabilities. Right, so if you sample again u the way we did it in the previous slide, in this second interval, then the state that you will return will be basically x equal to 2. Okay, can we do this inversion of the CDF for the for continuous random variables? And of course the answer is yes. If you do have the CDF for continuous random variables, it's actually straightforward. And before I do the derivation, let me just introduce some notation, if you like, or rewriting of certain integrals. So this is the CDF of some random variable x that has a PDF pi of x. So this is, the CDF is nothing else by definition but the probability of capital X being less or equal to little x. And that's my definition on the right hand side of the CDF the way you know it. But notice how I am writing here. Instead of having to integrate from minus infinity to x, I plug in this indicator function of u being less or equal to x, and I write the limits of integration from minus infinity to plus infinity, and I'm going to make use of this in my derivations today. Notice the two integrals are the same because this indicator function is 0 if u is greater than x. So to get non-zero values, you have to integrate from minus infinity 2x, and this is what you see on the right hand side. But this is sort of nicer because the limit of integrations are include all the support of the random variable here, going from minus infinity to infinity. Okay, so here is my algorithm. Literally a very simple one-line algorithm. Select u from a uniform random variable, you sample u, and then you compute the CDF inverse at the value u, and what it returns a sample from the actual distribution pi. Now, to prove of this, we're going to have to prove that according to this derivation, the probability of capital of X being less or equal to little x is nothing else but the CDF of the distribution pi. Now, you will agree with me that if you think that the CDF of a continuous random variable is a monotonic function, right, you will agree with me that the probability of capital X being less or equal to x, it is the same as the probability of u, that's my uniform random variable, being less or equal to the CDF value computed at x. Right, so one way is to look on the horizontal axis on a plot of the CDF and say you look at the probability of capital X less than equal to x, and another way to look at this probability is to take the probability of u being less or equal than the CDF value computed at x. Now, u is a uniform random variable, and if I use this nice formula, I can, because pi of u for the uniform random variable would be 1, so I can write this with the indicator function that u is less or equal to the CDF at x, and immediately, because this is 0 if u is greater than f of x at little x, so this is the integral of du from 0 to the CDF at little x, so that gives you the CDF at x. So effectively, we have proven that the probability of capital X being less or equal to x is the true CDF of pi. So effectively, the sample X that we generated is a sample coming from the distribution of interest. So here is how the algorithm looks like. Literally, trivial schematic here. This is your CDF. You sample u from 0 to 1. You invert the CDF. You get a value y, and then you set your sample x equal to y, and that's a sample then from the underlying distribution that has CDF, this capital of f. So the algorithm literally doesn't have anything more than that, and this equation is basically precisely what I showed you in the previous slide. Okay, so this is this reverse sampling, all right, that we use to compute, to sample from continuous distributions with known, right? This is very important, with known CDFs. Okay, so here's an example for a Gaussian on how you're going to sample from a Gaussian. So on the top you see the Gaussian, on the bottom you see the CDF. So you sample uniform random variable from 0 to 1, you invert the CDF, and then what you return is basically a sample that comes from the Gaussian. Very simple, and of course you know that the CDF for the Gaussian, we know it analytically, so we can, this is an algorithm we can implement with this. Let's see a little bit more complex distributions, and this example includes the exponential distribution. For those who forgot, I remind you, the exponential distribution has support from 0 to infinity, has parameter lambda, and it is lambda e to the minus lambda x. That's our PDF. So if you look at the CDF, of course, for x negative or 0, this is 0. For x positive, it's 1 minus e to the minus lambda x. And that's very easy to invert, right? So if you take this to be equal to u, then you can solve x in terms of u, and that will give you a sample coming from this exponential distribution. So this is what I literally do here. I set this to u, where u is a sample from 0 to 1. Then I solve for x, and I get minus 1 over lambda log of 1 minus u. So that's my inverse CDF computed at u. And you know now that this is a sample from the exponential distribution. So effectively, what I show you here is equivalent to this, that if you have u to be a uniform random variable from 0 to 1, then minus 1 over lambda log of 1 minus u is the exponential distribution with parameter lambda. Okay, you can actually show, and it is given on this slide, there's really not significant calculation or anything like that, that you can derive another similar equation where instead of log of 1 minus u, you use log of u. So you can show that minus 1 over lambda log of capital of u, where u is a uniform random variable, gives you the exponential distribution with parameter lambda. And again, the proof is rather trivial, following this calculation that you see on the bottom, and you can show that x is it's the exponential distribution. Okay, so here what I have is basically a way to generate a histogram of the exponential distribution with parameter lambda by sampling from the uniform distribution, taking the inverse CDF, plotting the histogram, and that's exactly what you see on this slide. So I am not going to repeat the calculation. This is the inverse method for the exponential distribution, and again, the only thing that you need to be able to compute to use this method is you need to have the cumulative density function for the distribution of interest. All right, so let us try to do another example. And actually, looking at this example, this is something that I will use in the follow-up lecture on a much more complex algorithm for sampling. So you may want to remember this example. So here is what I want to do. I have these samples xi that come from some probability density, little f of x, and with a known cumulative density capital F of x. Okay? Now what I want to do is I want to sample from the underlying distribution of this random variable z that is the maximum of x1, x2 to xn. And I'm going to try to do this with the inverse method. Remember, to apply the inverse method, you need to know the CDF of your random variable, so we need to compute the CDF of z. And the only thing we know is the CDF of each of these x's, that they are IID. So the CDF of z actually can be produced simply by definition. So this would be the probability that x1 is less than z, x2 less than equal to z, and xn less or equal to z. And because x1 to xn are IID, I can write this as this product of these individual probabilities. And each of them is nothing else but the CDF of each of the xi's computed at z to a power n. So I am done. I have the CDF of the distribution of z, and the only way to be able to sample, will be to actually invert this CDF. So what you need to do is set this equal to u, where u is a sample from 0 to 1, and then effectively invert that to compute z. And this is what I have in this equation, right? So if you take u to be a sample from the uniform distribution, then you have u to 1n, and then you are going to have to invert this cumulative density of the x variables, and that will give you a sample of z, and I can formally write this as z equal the inverse CDF of x, u to 1 over n. And this is a nice way to write it because, it basically tells you if you have this uniform random variable u from 0 to 1, that mapping takes you to the to the random variable z. So we can produce samples of z by sampling the uniform distribution from 0 to 1. Now, we need to mention that this is not the best method, and it's not the best method because it requires that we know the CDF. Obviously, most of the examples that you will see this method applied will be for univariate distribution. So you may wonder, how do I actually going to apply this on multivariate cases? And of course, all of these limitations means that the method is used only for academic examples and is not going to be of use for realistic problems in the remaining of the course. However, there is a useful idea that comes from this inversion method, and the useful idea is that if you sample somehow from a simple distribution through some transformation, in our case the transformation was that inverse CDF, we can go to any other distribution. So the question is, can we actually use some more complex transformations beyond the inverse CDF so we can start learning or generating samples for complex distributions? And the answer is yes. That's what goes with the name of transformation methods. So to motivate this, I am going to write down the two equations that I had before. So if u is a uniform random variable from 0 to 1, then x given by minus 1 over lambda log of 1 minus u is the exponential distribution with parameter lambda, and minus 1 over lambda log of u is the exponential distribution with parameter lambda. So the idea here is, if u are samples from a uniform distribution from 0 to 1, then these x's are samples from the exponential distribution with parameter lambda. Now, can we actually extend this? So let me give you some transformations. Let's say, so based on the formulas on the top, we already know how to produce samples from the exponential distribution, right? And we know because samples from the uniform distribution and then these log maps will give us samples from the exponential distribution. So here is some transformations that the only thing they require are samples from the exponential distribution with parameter lambda equal to 1. You can show the following. That if you take 2 times the sum of xi's, where xi's are sampled from this exponential distribution with parameter 1, so if you take 2 times this sum, and the sum here, this index nu, is integer, then actually what you get is you get samples from the chi-square or chi-square distribution with 2n degrees of freedom. Similarly, if you take this sum of xi's from I1 to alpha, assuming alpha is an integer, times beta, then you do get samples from the gamma distribution with parameters a and b. And then if you take this ratio of these two summations, then you get a sample from the beta distribution with parameters a and b. So effectively, we can go all the way from samples from the uniform distribution to the samples from the exponential distribution, and from there we can generate samples from the chi-square distribution, the gamma distribution, and the beta distribution. Of course, the only limitation on what you see on this slide is that these parameters that you notice in the gamma and the beta distribution have to be like you see here, we have a summation. Obviously, alpha has to be an integer, and you see here in defining the beta distribution, alpha and beta have to be integers. So obviously, this technique up to now will not be able to generate for us sample for an arbitrary set of parameters alpha and beta for the gamma and beta distributions. Okay, so we will not be able to sample beta and gamma for non-integer parameters. So let's try, since we know how to sample from the exponential distribution with any parameter lambda, let's see how we can sample using what we learned, how we can sample from the univariate Gaussian. Okay? Now, I know you're going to tell me you know the CDF of the univariate Gaussian, you can use the inverse mapping, and I already saw you a schematic, but let's see another way to sample from the univariate Gaussian. So let me use the following, and there is a link here on Wikipedia for the non-believers. If you take x1 to be a sample from the standard Gaussian, and x2 to be a sample from the standard Gaussian, and similarly xn, a sample from the standard Gaussian, then x1 squared plus x2 squared plus xn squared turns out to be a sample from the chi-squared distribution with n degrees of freedom. And it turns out that if you take two samples from the univariate Gaussian, x1 and x2, then x1 squared and x2 squared gives you the chi-squared distribution for 2 degrees of freedom. It turns out to be the exponential distribution with parameters 1/2. So why is this relevant? So let me pose the problem of interest. Let's say that I want you to generate for me two samples from the standard Gaussian. So I want samples, two independent samples, x1 and x2, from the standard Gaussian. So here's what I'm going to do is I'm going to take these samples x1 and x2 as if they were Cartesian coordinates, and I'm going to define the corresponding polar coordinates r and theta, the radius and the angle. So r squared is x1 squared and x2 squared. And immediately you see from this theorem here that if x1 and x2 are standard Gaussians, r squared then is going to be a sample from the exponential distribution with parameter 1/2. And I remind you, by the way we derive samples from the exponential distribution with parameter lambda, this will be basically -2 times log of u, where u is a sample from the uniform distribution with parameters, is uniform distribution from 0 to 1. Okay? You remember again from the previous slide on how we derive samples from the exponential distribution. So if we want a sample from the exponential distribution with parameter lambda, one way to do this is to take -1 over lambda log of u, and that would be a sample from this exponential distribution. In our case, lambda is equal to 1/2. So r squared then is going to turn out to be -2 log of u, where u is a sample from the uniform distribution. So here it is. Here's the algorithm on how you're going to generate samples of x1 and x2 that are independent samples from the univariate Gaussian. You're going to take a sample u from the uniform distribution 0 to 1, and you are going to compute a sample from the exponential 1/2. So a sample of r squared, that is -2 log of u1. You're going to square that, and that's a sample of r, right? And then you're going to need to define x1 and x2, you're going to need r cosine of theta and r sine of theta. And what you can do is you are going to take the theta to be a uniform random variable from 0 to 2 pi. And the way you're going to generate this is by taking a sample u from the uniform random variable from 0 to 1 and then multiply by 2 pi. So effectively, these equations that you see here are transformation equations that allow me to sample u1 and u2 independently from the uniform distribution in the interval 0 to 1, and then with these equations I can generate samples of x1 and x2 that they are from the standard Gaussian. And actually you see a schematic that shows you a histogram of a standard Gaussian generated this way by starting with samples u1 and u2 of the uniform random variable in the interval 0 to 1. Okay, let me show you another way to generate these samples for the univariate Gaussian. So we're going to generate two independent samples from the univariate Gaussian, and this algorithm that I'm going to describe goes under the name of Box-Muller algorithm. You remember when we discussed about the Monte Carlo experiments and how to sample uniformly on a circle. So the way we did it is, we consider the square where the circle is inside, right? And we sample uniformly the square, and then effectively all the samples that they were not on the circle, we got rid of them, we disregard them. So effectively, if you think of a unit circle, right? If you want to sample, Z1 and Z2 on the unit circle, what you can do is you can envision this experiment where you take samples on this box surrounding the circle, and then you count the number of samples that are inside the circle. So what I have here is I have the probability of Z1 and Z2 being the indicator function that Z is inside the unit circle divided by pi. Okay? So effectively what you need to simulate this is you need to sample uniform random variables in the x and y directions if you like, all right? And then from those uniform random variables you define the indicator function that allows you to keep only those samples that are inside the the circle, and then I have to divide this by 1 over pi, right? So for this distribution to be normalizable, all right? So if you take the integral of this inside the circle, you're going to get 1. So I need this 1 over pi for normalization purposes. Okay, so here is the idea, right? So we want to use these sample z's, okay, that they are uniformly sampled in a unit circle, in a unit radius circle. We want to use this distribution of Z1 and Z2 to generate 2 samples from the univariate Gaussian. Okay, so here's how I'm going to do it. I'm going to do it with 2 sets of transformation. One of these transformations is going to take me from Cartesian coordinates Z to polar coordinates in a similar way that I worked on this before. The Jacobian of that transformation is equal to R. All right, so if you take, this is the determinant of del Z1, del R, del Z1, del theta, del Z2, del R, del Z2, del theta. If you do the calculation, this Jacobian comes to be R. And then I'm going to define another transformation that takes me from R and theta to Y1 and Y2 that look as these 2 otherwise complicated and unassuming expressions. And you can actually show that the Jacobian of the transformation that you see here is equal to minus 2 over R. Right? So if you take derivatives of y1, y2 with respect to R and theta, and you form the this Jacobian, you take the determinant, it turns out to be minus 2 over R. So now what I'm claiming is that if I compute the distribution of y1 and y2 using the distribution of z1 and z2, which is, you remember, the uniform distribution over a unit circle, then the distribution that I'm going to get corresponds to 2 uncorrelated, univariate Gaussian distributions. So let me do the algebra so you can see exactly what I'm talking. We're going to try to go from z1 to z2 to y1 and y2, and remember how the probability law, the transformation works. So here you're going to need the Jacobian of z1, z2 with respect to R and theta, and then here you're going to need the inverse Jacobian of y1, y2 with respect to R and theta. Actually, a good way to see that this is correct, right? If you write this as the Jacobian of R and theta, del R theta, and on the denominator you have del of y1, y2, you notice this del of y1, y2 multiplies the probability of y1 and y2, so you get the probability mass of y1 and y2, and then on the if this R and theta goes in the numerator, you can think of this cancel out here, and then what actually you get is you get the probability mass of Z in Z1, Z2. So this equation looks correct. If you plug in this Jacobian, if you plug in this determinant of this Jacobian, what you get is you get r squared over 2 pi, and it turns out if you take y1 square and y2 square, right, so you have cosine square and sine square, this will give you 1. So what you actually get is you get that r squared over 2 pi is nothing else but 1 over 2 pi, the exponential of y1 square over 2 and y2 square over 2. Please do the algebra, take the squares of this. You have a log here, so r squared will give you an exponential, and this is what you get. So what actually we're getting is we're getting two univariate Gaussians. So effectively, we have been able, by sampling, by sampling in uniformly on the unit radius circle with the transformation first to polar coordinates and then to this y1 and y2, we're able to produce two independent samples of the univariate Gaussian. Okay, so that's nice. Now, if you have two correlated random variables Z1 and Z2, so if we have correlations now in my joint distribution of Z1 and Z2, the way to generate correlated samples X1 and X2 is through the transformations that you see on this slide. Okay, so before we said that we can sample, right, from the standard Gaussian, right? That's the univariate standard Gaussian. We can sample with a Box-Muller algorithm. Then if you have samples of Z1 and Z2 coming from the standard Gaussian, and you have, what correlation rho you want between X1 and X2, and you want to have a mean mu1 and mu2 and standard deviations sigma 1 and sigma 2, then these two transformations will give you samples of the joint distribution of X1 and X2 with means mu1, mu2, standard deviation sigma 1 and sigma 2, and correlation rho. You can actually evaluate the expectations and the variance of X1, X2 and the covariance of X1 and X2 to verify this. So what I'm going to do is I am going to show you plots that are generated by taking samples with various means for this Gaussian that has mean mu1 and mu2 minus 1 and 1, and it has a covariance matrix given by this. Okay, and I'm going to generate this with a little MATLAB program using using different calls to different routines that MATLAB has. But actually, before I do this, let me try to generalize for a second and tell you how you can actually use univariate samples from the univariate Gaussian to generate samples for the multivariate Gaussian. Okay, so let's get that out of the way, and then I will show you the plots for the bivariate Gaussian density. So if you have the multivariate Gaussian and you want to generate samples from it, here is an algorithm. Draws this from the standard Gaussian, right? So if this is a 10th dimension Gaussian, draw 10 samples from the standard Gaussian. Do the Cholesky decomposition of the covariance matrix sigma, so that is S transpose, all right? And then set the following simple transformation. So remember the vector Z is this vector of each component is a sample from the standard Gaussian. Then I'm claiming that X equal mu plus SZ is actually a sample from the Gaussian with mean mu and a covariance sigma. With a mean you don't have a problem because these Z's have all mean 0, you can see the expectation of x is equal to mu. And when it comes to the covariance, you can use the definition, and this is what I have here. X minus mu is SZ and SZ transpose. And then you have the expectation of ZZ transpose, right? The expectation of ZZ transpose, and that is the identity metrics, right? Because these are uncorrelated random variables, and the standard deviations here, they are all coming from the standard Gaussian. So this is I, then I have SS transpose, and this is equal to sigma. So the covariance of the generated X, right? X follows, has a covariance, these samples have a covariance sigma. So we have mean mu, so these X's are samples from the multivariate Gaussian with mean mu and a covariance sigma. So what you see here is different MATLAB plots, and I can see here it says these are plotted using univariate samples, all right? And actually this particular calculation with univariate samples, if you look at the computer program, is literally it does this calculation. If I can go back, it takes samples from the univariate Gaussian, and then it generates samples from the bivariate Gaussian. So this is what it refers here as using univariate samples. And this histogram that says PDF with bivariate samples is using the routine in MATLAB that gives you directly samples from the multivariate Gaussian. That's the function, if I remember, MVN RND, right? Multivariate normal random variable, MVN RND. So this gives you directly samples, bivariate samples. And again, you see the histogram of the two-dimensional Gaussian generated with two different ways. Of course, the number of samples going up, the two approximations could be practically the same. And again, the same plots here with another implementation, okay, of the same problem. Okay, let's now move to discuss a much more important category of algorithms, and this category of algorithms goes with the name rejection sampling. So we need to pay attention here to the notation, because we're going to be introducing lots of ideas that are going to be essential for more complicated algorithms. So what is the problem? We need to sample from pi of x. The support space is this calligraphic x, and we're assuming that x is only known up to some proportionality constant. So I am going to use pi star to identify the anormalized distribution pi. All right, so pi star is the anormalized distribution pi. Okay, and so we will see if we can actually work directly with pi star without the need to know the normalization factor of pi. All right, so idea number one, which is going to be essential in many algorithms, is rather than sampling directly on pi, we're going to sample from some other distribution that we call it the proposal distribution. And I denote this distribution Q of x. And even though we sample from another distribution, hopefully an easier distribution, the idea will be that some of those samples may turn out to be samples from the true distribution pi of x. Okay? So for now, we're going to sample from some other distribution Q of x. We call it the proposal distribution. And let's assume also that Q is known up to some normalization constant. So we really, let's say, know only Q star and not the normalized Q. To make this rejection sampling algorithm to work, we need to have a fundamental constraint in the algorithm, and this fundamental constraint says basically that Q of x needs to dominate pi of x. Okay? If you try to interpret this in an alternative form, effectively pi star of x has to be less than some constant times q star of x, where that constant is greater than this m. Okay, so q has to dominate pi of x. So if you think you're plotting, if these distributions are univariate distributions, and I'm going to show you a schematic soon, then q has to be on the top of pi, which means q needs to have fatter tails than the distribution pi. And of course, from what you see here, in the regions where the distribution pi is positive, q star also has to be positive. Okay, so these are the fundamental constraints to make this rejection sampling algorithm useful. We're going to need q to dominate pi, and the domination is defined with this equation that you see here. Okay, so what's the algorithm, and how does it work? So here's the algorithm, right? We want to sample from pi, but it's easier to sample from q. So what I'm going to do is I'm going to start as follows. I'm going to take a sample from the distribution q of y, and also I'm going to take afterwards a sample from the uniform distribution from 0 to 1. So y is a sample from q of y, and u is a sample from the uniform distribution. Then I am going to accept this sample y, and I'm going to set my sample x for the distribution pi of x equal to y, but I will accept it only with probability that is pi star of y divided by m prime q star of y, where m prime is the constant that we had defined in the inequality that I introduced in the previous slide. Okay, so rather than generating any sample from q of y and saying, oh, that's my new sample for my distribution pi of x, we're going to say, no, you're going to accept this sample y with this probability, all right, where again m prime has been defined by this equation that defines how q dominates pi of x. Now, when I say you accept the sample y with this probability, effectively, and that's where the use of the uniform random variable comes, that implies that if u is less or equal to this number here, then you accept y, otherwise you reject. Okay, so the accepted x is actually a sample from the true distribution, and obviously you can appreciate here that if this constant m prime is very high, right? So if you say, oh, I'm going to bound this by 10 million times some Gaussian, that is not going to help you, because if m prime is huge number, then this number here is very small, and that means you'll be accepting with probability basically 0, so you will keep sampling from q, and most of the time you will be rejecting the samples because they would not be the right samples for your distribution pi of x. So the idea of this constraint of q dominating pi, this bound here has to be as tight as possible, and m prime it has to be as small as possible to make this algorithm to be an efficient algorithm. Now, the new ideas that are introduced by this accept-reject algorithm, there are two, and they're going to be fundamental in many aspects of the course. Right? So the first one is, don't sample from pi, sample from q of x. So that's the idea of the proposal distribution. The second is, do not accept the samples y from q of y, but don't accept all of them right away, but accept them with some probability. That's the acceptance probability that I call here pi star of y divided by m star q star of y. So let me show you pictorially this algorithm. So here is my distribution pi star. Again, that's my normalized distribution, and the dotted is m star q star. M star is some constant, that I selected in such a way that I am above the distribution pi star, but not too much above, right? My distribution Q of y is the proposal distribution that the assumption is that it's easy to sample from. So here's the algorithm. You sample a y, and this is what I have here. I'm sampling some y from the distribution Q of y, and I'm also sampling u from the uniform distribution, and then I'm checking if u is less than pi star of y divided by m star q star of y. So effectively I'm checking if u times m star times q star of y, and that's this dot point here, that's m prime q star of y times u. So I am checking if this is less than pi star at this location of the sample y. So if the answer is yes, I accept, and this is what I have here. If I am above pi star of y, then I reject. Okay? So if m star u times q star of y falls within the underneath pi star of y, we accept, otherwise we reject. Okay, so, and again, both the distributions we have up to now need to be known up to their normalizing constants. By the way, when you look at these equations, especially the probability of acceptance, again, if you don't see m prime there at all, just pay attention to the way the distributions pi of y and q of y are defined and which one of them is normalized or not. And you will see that at the end of the day, all of these algorithms fall within the notation that I'm using in the slides. So I'm going to try to stick with this notation as much as possible to avoid any confusion. All right, so let me prove, why is this algorithm working, right? So, we have a very nice algorithm, but somebody will say, I don't believe a thing. Why with this acceptance probability is actually a sample from the true distribution. So let's try to actually prove this. All right, so let me, so we sample y from q of y, and we sample u from the uniform distribution, and we said if u is less than this, then we accept y, and we set x, that's our sample from pi of x, to be equal to y. So let me define the following. I'm going to define some indicator function that I call it j here. J, so it's 1 if the proposal sample is accepted, 0 otherwise. And what I'm going to try to do is I'm going to try to compute the probability of a sample being accepted. And actually this will be very useful as you will see very shortly. So this is the probability that the sample is accepted with this algorithm that I introduce. Now, I can write this using the product rule of probability and marginalization and the sum rule of probability as well. So I can say I can write this as the integral in y of q of y times the condition probability of j equal to 1 of 1 given y. Okay? Nothing fancy, right? I am using both the product and the sum rules of probability. Now what I'm going to do is I'm going to start substituting things in this definition here. So what is q of y? Q of y is, by the way here, notice because I'm sampling y from q of y, right? I use directly q of y even though I know only q star. Okay, but this is the correct definition of the proposal sample being accepted. So q of y is q star divided by the normalization factor, right? That's the definition of normalization. And the probability of accepting a sample y is nothing else but pi star of y divided by m star q star of y. You remember this is the probability of, that's what my algorithm, right? That's my algorithm. That's the probability of accepting the sample y. So this is what I have. All right, so let's see what type of simplifications we're going to get. Q star of y and Q star of y are going to cancel out. In the numerator, I'm going to get the normalization factor of the distribution pi of y. So this z that you see here is pi star dy integral in the support space. And then in the denominator, I'm going to have m prime times the normalization factor of Q star. So the probability of acceptance is given by the ratio of the normalization factors of pi and Q, and then there is an m star in the bottom as well. All right, let's prove now the whole algorithm, right? So let's find what is the distribution of x, assuming that the y sample that we got was accepted. And if you remember, if we accept y, then we set x equal to y. So I am using again the product rule of probability. And literally, if I can go here, this looks like the Bayes rule, right? I'm inverting my probabilities. So here I had the probability of x given j accepted. So I'm writing here the probability of j accepted given x times the probability of x divided by the probability of acceptance. So let's work on term by term. So first I have the probability that the sample x equal to y was accepted, and this is my acceptance probability evaluated for y equal to x. All right, that's the first fraction that you see here. And then I have the probability of x, and that's of course q of x, because x and y are sampled from q of x. And then on the denominator I have the probability of acceptance, and that is the normalization factor of pi divided, and this goes in the numerator, m prime times the normalization factor of q star. All right, so let me try to see what is going on. M prime and m prime are going to cancel out. And then what I have here is a q star divided by the normalization factor of q star. That will give me q, so q is cancelled out. So what I get is pi star over z, which is pi of x. So the probability of x, given the fact that I accepted x, turns out to be pi of x. All right. So effectively, we are sampling. If x is accepted, x is a sample that comes from the true distribution of interest, pi of x. So that's the end of the proof of the algorithm, and I summarize the result, the intermediate result that we got in this derivation, that the probability of y accepted is given by the normalization factor of y divided by m prime times the normalization factor of q. And I remind you that if this constant is very large, so if you have done very bad design of how you dominate the distribution pi by selecting very big m prime, then the highest m prime is, the lowest the probability of acceptance. So most of the time you'll be rejecting the samples, so that is not going to be an efficient algorithm. If you get confused with this notation on this slide and the proof that this algorithm does give you samples from the true distribution, I provide you another proof in this slide. Practically, there is nothing different, what I actually, let me just go very fast, right? Before we compute it directly, what is the probability of x if y has been accepted, and we saw that to be pi of x. So let me actually work with the CDF. So let me work with the probability that y will be less or equal to little x, assuming that y has been accepted, okay? And I am going to show you that this probability is the same as the probability of capital X being less or equal to x, and that's the CDF computed at x, right? So effectively, I generate samples from the correct probability distribution, and the way that I show this is again a similar calculation to what we had in the previous slide. So here I have the probability of y being less or equal to x and y accepted. So how do I write this? I have the probability of y being less or equal to x. So that's this integral that you see here from minus infinity to to x, okay, and y comes from the distribution q of y dy. All right. So this is it reminds you basically the CDF computed at x. This is what I have. This integral q of y dy, and then I have y accepted. And y accepted, I write it using this indicator function that y is accepted when u is less than pi star divided by m star q star of y. So if u is not accepted, this is 0. So I have u coming from the uniform distribution. This is my indicator function. So this is the joint probability of capital Y less or equal to x and y accepted. Now, because this indicator function is 0 when u is greater than this ratio, so the integration in u will happen only from 0 to this pi star divided by m star q star. So this is what I get. And then I have times q of y times dy. And q divided by q star, right? Q divided by q star will give you the normalization factor of q. On the numerator, you're going to have the normalization factor of pi. So what you have is, you have the normalization, on the numerator, wrong, right? So let me correct. On the q over q star will give me the normalization factor of q, and in the numerator I'm going to have the integral of pi star of y dy from minus infinity to x. So this reminds you like the CDF of pi of x, but the difference here is this is the anormalized distribution pi star. So we already proved that the probability of y accepted is given by this ratio. This is what I had before. And now what I'm going to do is I'm going to use the product rule of probability. And this is what I want to compute, right? So this is written as the joint probability of y being less or equal to little x plus y accepted divided by the probability of y accepted. I substitute this in the numerator. I substitute this in the denominator. And I see a lot of cancellations. M prime is cancelled, Q star is cancelled. And then I see pi star divided by the normalization factor of pi star, which is pi of y. So immediately I see the CDF of the distribution pi of x. So the probability of y being less or equal to x, given that y is accepted, is the CDF of pi of x, and so I am proving basically that the probability of y being less or equal to x, and given that y is accepted, is exactly identical to the probability that capital of X is less or equal to little x, which means the algorithm works, and I do sample from the correct probability distribution. Again, you have two alternative proofs. The main complication is understanding how this double integral comes, and a similar calculation was in the previous slide. So whatever of the two derivations works for you. One derivation works directly with densities, the other one works with CDFs. So whatever you feel more comfortable, you can understand one or the other derivations, but they're in principle equivalent. All right, so we computed the probability of acceptance, and we showed that this is the ratio of the normalization factor of pi divided by m prime divided by the normalization factor of q star. And now what I want to tell you is that if you take one divided by the prior probability, by this probability of y being accepted, effectively what you get is you get an unbiased, you get basically an estimate of the expected number of trials before a proposal sample is accepted. Okay, so let me repeat this. If you take 1 over the probability of y being accepted, that gives you the expected number of trials before you accept a candidate from the proposal distribution. Okay, now you may say, that's weird, from where is that coming? Why 1 over the probability of acceptance gives me the expected number of trials before I accept a sample? And the proof is actually very simple. Let's say that you are looking at an acceptance in the kth sample. What I mean with that is you are sampling once, you reject. And you reject if this is the probability of acceptance, you reject with probability 1 minus gamma. Then you sample again, you reject with probability 1 minus gamma, so you have the total 1 minus gamma square probability. And then at the kth sample, you accept. So the probability that the kth sample is going to be accepted, that the kth proposal from the proposal distribution is going to be accepted, it is this geometric, it follows a geometric distribution, and the probability that the kth proposal is accepted is 1 minus gamma to the power k minus 1 times gamma. So you reject k minus 1 times, you accept the kth time, and here is why 1 over the probability of acceptance is the expected number of trials before you accept a candidate from the proposal distribution. If you look at Wikipedia or in your probability book, you will see that the mean of the geometric distribution that you see here is 1 over gamma. So immediately you can see that the expected number of trials before accepting a candidate proposal is 1 over gamma, and gamma is given by this formula that you see here. So effectively the number of trials before accepting a proposal, you can think of this as being an unbiased estimate of 1 over the probability of accepting a candidate. Okay, let's do an example, right? So we can make things a little bit more concrete. So let's say that my underlying distribution is a beta distribution with parameters 3 and 2, and I take here, I know the normalization factor, so pi and pi star equal to the same thing. Now, this is my beta distribution, and if you try to compute the maximum of the beta distribution, you will find, right, if you try to compute the maximum of the beta distribution, you will find that the value is 48 over 27, okay? So effectively, what I can do is I can use as a proposal distribution the uniform distribution that actually you see here, all right? And then this inequality that I had to, you remember, Q has to dominate pi, and the way it dominates pi is because pi is less than 48 over 27 times the uniform distribution, which is 1. And symbolically, right, this is m times q. And by the way, q and q star here is also the same thing. They are both normalized. And now my algorithm becomes trivial. To be able to sample from the beta distribution, what I need to do is sample from the uniform distribution from 0 to 1, and then accept or reject with the underlying probability distribution that we showed before, which is, you remember, the normalization factor for pi star divided by m prime divided by the normalization factor of q star. So really, in this problem, the probability of acceptance is 1 over m prime, where m prime is 48 over 27, okay? So effectively, we are accepting with probability 27 over 48. And the histogram that you see here generated, all right, and is given on the left, and on the right you actually see the empirical measure of the beta distribution generated with samples following this rejection sampling algorithm. Let's do another example that looks a little bit more complicated, but it's actually nothing fundamentally difficult. Let's say that we have this univariate distribution that looks like a Gaussian, but then it has this oscillatory magnitude here that involves sines and cosines in some complicated way. So I am going to use as proposal distribution my normalized standard Gaussian into the minus x squared over 2, and you can see the way Q dominates pi can be derived rather simply because you notice if you look at pi star, right, this sine term is less than 1, this second term is less or equal to 3, and then I have this is less or equal to 1. So effectively pi star over Q star will give me this bracket, and if you take the maximum value of that bracket is really 5. So effectively my equation for Q dominating pi is given here with coefficient m star equal to 5, and I am plotting actually this 5 times e to the minus x squared over 2. I am plotting it, as you see, as an envelope to this underlying complicated distribution from which I need to sample. So we are done. What you need to do is you need to sample from the univariate Gaussian, and then you accept or reject with the corresponding probability that we have seen from the rejection algorithm, and you're done. All right. And now you notice there is a lot of little dot points here. You may wonder what those dot points are, and those dot points are. You remember when I showed you this, the first slide on the rejection algorithm, we were computing this probability of acceptance, and I said that to accept, U needs to be less than pi star of y divided by m star q star of y. So in principle, we were accepting if U times m prime times q star of y is less than pi star of y. So literally what I am doing here, I am taking the points x that I sample and the corresponding values of m, which is 5, times my uniform sample, the sample from the uniform distribution, okay, times, U is the sample from my uniform distribution from 0 to 1, and this is q star of x. Q star is my standard Gaussian here. So if these points fall within the domain with underneath this complicated pi star distribution, then according to the rejection algorithm I accept. If they fall above, we reject. So what you see on this plot is out of 500 samples, it shows here the samples that are below this pi star distribution. So these are samples. So the corresponding x location gives you the samples x that the algorithm says that we should accept. Okay. So again, this is a nice way to geometrically, with these points, plot this x, m times u times q star of x. And if those are within the distribution pi star of x, are below pi star of x for each x, where you sample, then you accept, otherwise you reject. Okay, so and what you see now on this plot here is a histogram from the generated samples using this accept-reject sampling technique. So even this complicated but univariate distribution can be sampled nicely with the accept-reject algorithm. Now, before I finish with the lecture today, and we will continue soon with the second part of the accept-reject sampling algorithms, let me just say that there are two things that need to stay in your mind. This basic idea that now we have a proposal distribution, so we sample from something else. We sample from Q of X that's easier to sample from, but we don't accept all the samples. We only accept with some probability, and that probability was tested using uniform random variables. And then we prove basically that the algorithm works under not very complicated conditions to satisfy, and the key condition to satisfy was that the distribution Q, the proposed distribution, needs basically to dominate the distribution pi, in the sense that pi star is less than some constant times Q star. Okay? And remember, all the calculations we did were without the need to know the normalization factors for the distribution pi star and Q star. So what we will do in the next lecture, we will I will give you some efficient algorithms to sample from the gamma distribution, and then we will discuss some further sampling techniques that provide extension of the ideas that we have learned up to now. For now, happy readings. Bye.